I want to talk today about aromatic compounds. I want to talk a little bit about their reactivity and what makes them different from other organic compounds, but I'm going to focus mostly on what's required for the compound to be aromatic and how to recognize an aromatic compound. I want to start out by talking about and looking at the prototypical aromatic compound, benzene, and compare it to another compound with a double bond in it, this cyclic alkene. What I want you to notice is the cyclic alkene does the standard reaction that a cyclic alkene will do, and it gives you the dibromo compound with the bromines going in the opposite directions, trans-substituted. On the other hand, Br2 in the solvent CH2Cl2, you get no reaction at all. So benzene, the aromatic compound, is stable towards these reaction conditions that would react with a standard alkene. In trying to understand why benzene, or what benzene does that is different from other alkenes, I also want to look at this reaction involving the hydrogenation of an alkene. And we have H2, we have palladium catalyst, and the delta H for this reaction is negative 28.6 kilocalories per mole. Exothermic. And it's hydrogenation, and we get the product with no alkene, no double bond. I want to look at what happens if we have two double bonds. So if we have two double bonds in my ring and they're conjugated, I get a little bit of stabilization from the conjugation. If they were acting completely independently of one another, I would expect the value for the enthalpy of hydrogenation to be twice that of one double bond. So instead of being minus 28.6, it should be minus 57.2. So it's a little bit lower than that because we get some stabilization from resonance. This molecule is already a little bit lower in energy. Well, what happens if we put three double bonds in the ring? If we go to benzene, something really interesting happens, actually. So if we reduce benzene all the way down to cyclohexane, what we see is we get minus 49.8 kilocalories a mole of energy released. Well, that's less than if we reduce two double bonds. So the reduction of this first pi bond, going from benzene to the alkene with two double bonds in the ring, it's actually endothermic. It's so unfavorable to break up this benzene ring that we actually have to add energy to do it. And we get a total of 36 kilocalories in resonance stabilization. That's a lot of energy. And what I'm trying to point out to you with these examples is that there's something special about benzene and other aromatic compounds. We call these aromatic compounds. They are stable. They're more stable than you would expect. And in order to understand the stability, you really have to look at the molecular orbitals and how the lower energy orbitals are completely filled, but we're not going to worry about that today. What I want to do is I want to focus on the structural characteristics of the molecule that are required for a molecule to be aromatic. So let's look at some of that right now. The first thing that's required is that the molecule must be cyclic. For example, if we look at this molecule right here, it looks a lot like benzene, except I've removed one of the sigma bonds. If we look at the heat of hydrogenation for this, we can see it is minus 82 kilocalories per mole. We get about 4 kilocalories of resonance stabilization, not very much. For a molecule to be aromatic, it must be cyclic. The next requirement is that you need a continuous run of p orbitals in your cyclic molecule. So for instance, in this molecule, this is cycloheptatriene. You can see it has 3 pi bonds, but this carbon right here is sp3 hybridized. There is no p orbital on that atom. You need a continuous run of p orbitals on all of the carbons in the ring. All the other carbons have it, but not this one sp3 hybridized carbon. The next reason involves the number of pi electrons in my aromatic system. And the general rule is you must have 4n plus 2 pi electrons, where n is a whole number. What do I mean by that? Well, for benzene, we have 2, 4, 6 pi electrons. When n is equal to 1, 4n plus 2 equals 6. So this is an aromatic molecule. It has the right number of electrons. For this molecule, it has 10 pi electrons. 2, 4, 6, 8, 10. When n equals 2, 4n plus 2 equals 10, so this molecule has the right number of electrons. For this one, I have 18 pi electrons. I'm not going to count them. You'll have to take my word for it, or you can count them yourself. In this case, n equals 4. When n equals 4, 4 times 4 plus 2 equals 18. So this is an aromatic molecule. You have to have the right number of molecules in your aromatic system. What happens if you have the wrong number of electrons in your aromatic system, in your ring? Well, this particular molecule has 14 pi electrons. There's no whole number you can come up with where 4n plus 2 will equal 14. This is not going to be aromatic. We'll talk about this later. This is a kind of compound called anti-aromatic, but I don't want to worry about that right now. This has the wrong number of electrons. It's not an aromatic molecule. The last requirement is that the molecule must be planar. Now, this is a little bit harder to see when it's not planar, but I want to talk about this a little bit. Most of the time, this is not a problem, because most of the time the molecules are planar, because we're dealing with sp2 or sometimes sp hybridized molecules, which are flat, trigonal planar molecules for sp2 hybridization. But sometimes structural features of our molecule require that the molecule bends. For instance, in this molecule, cyclodecapentaene, these two hydrogens are so close to one another that if this was a flat molecule, they would literally crash into one another. So this molecule, even though it has the right number of electrons and it's cyclic, and the right number of pi electrons and it's cyclic, is not planar because these hydrogens are too close. So it twists out of alignment, and it's not an aromatic molecule. I want to talk for a minute about heteroaromatic compounds. We should probably explain what a heteroatom is. And a heteroatom is any atom other than carbon or hydrogen in an aromatic molecule. So in this case, this nitrogen is heteroaromatic. This oxygen is I'm sorry, I should say that differently. This nitrogen is a heteroatom. This oxygen is a heteroatom. This oxygen is also a heteroatom. Any atoms that are not carbon or hydrogen. And you can have heteroatoms in aromatic compounds. For instance, this first molecule, purine, is fairly easy to see. This nitrogen just takes the place of one of the carbons. This molecule, at first blush, might not appear to be aromatic, but if we draw this resonance structure, you can see that it can adopt a structure where all of the requirements for it to be an aromatic compound are met. The last thing I want to talk about today is instances where we have aromatic compounds that are charged. For instance, in this first example, the starting molecule, cyclopentadiene, is not an aromatic compound. We have the wrong number of pi electrons, and this is an sp3 carbon. We don't have a pi orbital on every carbon. But if we treat this with base, what happens is one of these hydrogens is removed. I get a lone pair, which is going to conjugate with the electrons in the ring. It's going to give me the right number of pi electrons, and this would be an aromatic compound. Similarly, chlorocycloheptatriene is not an aromatic compound. But if I lose, because this is an sp3 carbon, no pi orbital. But if I lose this chlorine, I get a carbocation. This carbocation has a p orbital on it. This is an aromatic compound. So I can have charged aromatic compounds.